Hi, this is the lecture on gas laws. There are many gas laws that we will study. We will study Boyle's law, Charles' law, Gay Lussac's law. We will study Graham's law of effusion, Avogadro's law. So we will look at gases relative to pressure, volume, temperature, moles, all of them together, just pressure and volume, just for volume and temperature, etc. A crash dummy can be used to test the effectiveness of an airbag because gases can be compressed. The airbag absorbs some of the energy from the impact of a collision. Airbags work best when combined with seat belts. Please get some paper out and take some notes while we do this so that you can hand it in for extra credit. I'll give you extra credit, and then you can also use it on your test, so I encourage you to do that. Recall that a gas can expand to fill its container, unlike a solid or liquid. The reverse is also true. Gases are easily compressed or squeezed into a smaller volume. Compressibility is a measure of how much the volume of matter decreases under pressure. Why does a collision with an inflated airbag cause much less damage than a collision with a steering wheel or a dashboard? When a person collides with an airbag, inflated airbag, the impact forces molecules of gas in the bag closer together. The compression of the gas absorbs the energy of the impact. Now, that's not the entire picture of how an airbag works. In physics next year, what you'll study is momentum and impulse and impact time. Very simply, the longer the impact time, the less forces are involved, the safer it will be, and we'll talk about that more in a little bit. There are only a few nitrogen and oxygen molecules in this model of air. At room temperature, the distance between molecules in a container of air at standard pressure is about 10 times the diameter of the molecule. Let's just talk a little bit about momentum. Momentum equals mass times volume. Mass times velocity. That equals momentum. So if you crash into a wall, you're going to change your momentum. You're going to go from 50 miles an hour, or 50 kilometers per hour to 0. Let's go back. Kinetic theory can explain why gases are compressed more easily than liquids or solids. Gases are easily compressed because of space between the particles in gas. Remember that the volume of the particles in a gas is small compared to the overall volume of the gas. So the distance between particles in a gas is much greater than the distance between particles in a liquid or a solid. Under pressure, the particles in a gas are forced closer together or compressed. At room temperature, the distance between particles in an enclosed gas is about 10 times the diameter of a particle. So momentum is mass times velocity. Change in momentum is when that goes to 0. A change in momentum is actually equals the impulse. So let's say the momentum is 10. Let's just say it's 10. It's going to be greater than 10, but we'll say it's 10. So 10 equals the impulse. Well, impulse equals force times time. You get it? Let's continue. Figure 2 is, as we saw before, is a model of air, an air sample at room temperature. Only oxygen and nitrogen, the two main gases in air, are represented. Note how few particles can fit into this relatively large space when the distance between the particles is reasonable for the size of the particles. So the change in momentum, 10, is going to equal force times time. All right? So write that down. That's where we are right now. Okay, good. Now, we want to calculate the force. It isn't practical to represent the actual distances between particles in all the molecular drawings of gases in this book. The drawings would be too large to easily fit on the page. For the drawings to fit on a page, the particles must be drawn closer together. So, if time is a small value, in other words, you hit a brick wall, then figure 4 shows what happens when a gas is added to an enclosed rigid container. Because the container is rigid, the volume of gas is constant. Assume also that the temperature of the gas does not change. Under these conditions, doubling the number of particles of gas doubles the pressure. Tripling the number of particles triples the pressure, and so on. Now remember, that's moles versus pressure. That's interesting, moles versus pressure. Okay, you get it? Moles versus pressure, you're increasing number of particles. With a powerful pump and a strong container, you can generate very high pressures by adding more and more gas. However, once the pressure exceeds the strength of the container will burst. Removing gas from the rigid container has the opposite effect. As the amount of gas is reduced, the pressure inside the container is reduced. So that's a relationship between moles and pressure. So you see that it's a direct relationship. When a gas is pumped into a closed rigid container, the pressure increases as more molecules are added. If the number of particles is double, the pressure will double, predicting what would happen to the pressure in the container if the number of particles were tripled, if the number of particles were cut in half. So moles is proportional, moles is direct. Moles and pressure are direct. Okay, spray can. The pressure of gas inside a new can of spray paint is greater than the air pressure outside the can. When the gas rushes through the opening in the top of the can, it propels or forces paint out of the can. As the can is used, the pressure of the propellant decreases, relating cause and effect. What happens when the pressure of the propellant equals the air pressure outside the can? Well, no spray is going to come out. If the pressure of the gas in a sealed container is lower than the outside air pressure, air will rush into the can when the can is opened. This movement causes the whoosh you hear when you open a vacuum-packed container. When the pressure of gas in a sealed container is higher than the outside air pressure, the gas will flow out of the container when the container is open. Aerosol cans depend on the movement of gas from a region of high pressure to a region of low pressure. High pressure to low pressure. And you'll find that there's going to be a decrease in temperature as well. That's Gay Lussac's law. If you put your finger near the nozzle, it's going to be lower temperature. Lower temperature. So the change in momentum equals force times time. So if I divide by a small time, I have a large force. Aerosol cans may contain whipped cream, hair mousse, or spray paint. Figure 5 shows how a can of spray paint works. The can contains gas stored at high pressure. The air outside the can is lower pressure. Pushing the spray button creates an opening between the inside of the can and the air outside. Interesting. More about spray cans than you ever wanted to learn. The gas flows through the opening to the lower pressure region outside. The movement of the gas propels or forces the paint out of the can. As the gas is depleted, the pressure inside the can decreases until the gas can no longer propel paint from the can. As they say when the plot is about to thicken, as the plot thickens. A piston can be used to force a gas in a cylinder into a smaller volume. When the volume is decreased, the pressure of the gas exerts is increased. Interpreting diagrams, what happens to the gas pressure when the volume is reduced from 1 liter to 0.5 liters. Pressure and volume, indirect, Boyle's law. This is Boyle's law. You can raise the pressure exerted by a contained gas by reducing its volume. The more the gas is compressed, the greater is the pressure that the gas exerts inside the container. When gas is in a cylinder, as in an automobile engine, a piston can be used to reduce the volume. The snug-fitting piston keeps gas from escaping as the cylinder moves up and down. Figure 6 shows a cylinder of gas under 2 different conditions. Now, I want to talk a bit about momentum. Momentum is important when understanding molecular theory, kinetic theory, and why an airbag works to help keep the driver and the passenger safe. Momentum is a quantity. It's a physical quantity. Mass times velocity. Momentum is mass times velocity. I have a mass and it's going at a certain velocity. It has a momentum. Now, if that object comes to a stop, then it's going to have a change in momentum. So, let's look at a simple idea. Let's look at a simple idea. Now, let's say we have an object. It has a momentum of 100. Now, we know that momentum is mass times velocity. I said that. So if the object stops, it has no momentum. So the change in momentum was, it was 100, now it's 0, so the change is 100. Okay, now, it's important to know that the change in momentum equals force times time. We all know what the word force means. The word force times time. Okay, now, change in momentum equals force times time. Now, let's say it took 10 seconds to stop. All right, force times time. So 100 divided by 10 is going to be 10. So it's going to have a force of 10. Okay, change in momentum, 10 seconds to stop, 100 divided by 10 is 10. So it has a force of 10. Now, let's reduce the time. Now let's say it stops in 1 second. Okay, so 100 divided by 1 has a force of 100. Okay, so I went from, I decrease the time, I increase the force. Decrease time, increase force. Okay, I had a force of 10, now I have a force of 100. Now, let's say the time is 0.1. All right, 100 divided by 0.1 is 1,000. Okay, now, let's say it's going to be 0.01. So 100 divided by 0.01 is 10,000. 100,000, a million, 10 million, 100 million, a billion. So as I decrease the time, I'm increasing the force. So let's say I have a car now, I'm in a car, and let's say I'm going too fast, and I hit a brick wall. That means that my stopping time was instantaneous. 0.001 seconds. So the forces are going to be enormous. The forces are going to be enormous. Now, that airbag, what's the airbag do? The airbag extends the time in which the body is coming to a stop. Crumple zones in the front of the car are increasing the time. Seat belts are increasing the time. Padded dash is increasing the time. Things are giving. So I increase the time, I decrease the force. I increase the time, I decrease the force. The change in momentum is going to occur. I could run into a haystack. I'm going to increase the time, I'm going to decrease the force. Increasing the time saves lives. Okay, now let's look at some actual information relative to physics, and then we'll go right back. All right, hold on. The change in momentum depends on the force that acts and the length of time it acts. As the figure shows, apply a brief force to a stalled automobile and you produce a change in its momentum. Apply the same force over an extended period of time and you produce a greater change in the automobile's momentum. A force sustained for a long time produces more change in momentum than does the same force applied briefly. So, remember I said, force times time equals change in momentum. High force, high time, high change in momentum. That's all we're talking about. So we're talking about actually how do we increase the change in momentum. So we're looking at the relationship between change in momentum and Ft. Large Ft, large change in momentum. When you push with the same force for twice the time, you impart twice the impulse. Impulse is force times time, and produce twice the change in momentum. When you push with the same force for twice the time, you impart twice the impulse and produce twice the change in momentum. Make sense? Impulse is force times time. Force times time equals change in momentum. Impulse equals change in momentum. Okay, so far so good. When you push with the same force for twice the time, you impart twice the impulse and produce twice the change in momentum. The quantity force times time interval is called impulse. In shorthand notation, impulse, Ft equals delta mv. Ft, force times time, equals change in momentum. I equals F delta t. The greater the impulse exerted on something, the greater will be the change in momentum. The exact relationship, impulse equals change in momentum, or Ft equals change in momentum. Force times time equals change in momentum. Delta is change. The Greek capital letter delta is change. I could actually say F delta t, but either way. The impulse-momentum relationship helps us to analyze a variety of situations where the momentum changes. Consider the familiar example of impulse in the following cases of increasing and decreasing momentum. To increase the momentum of an object, it makes sense to apply the greatest force possible for as long as possible. Greatest force possible for as long as possible. A golfer teeing off and a baseball player trying for a home run do both of these things when they swing as hard as possible and follow through, very important, follow through with their swing. The forces involved in impulses usually vary from instant to instant. The forces involved in impulses usually vary from instant to instant. Makes sense. A golf club that strikes a golf ball exerts zero force on the ball until it comes in contact with it. Then the force increases rapidly as the ball becomes distorted. The force then diminishes as the ball comes up to speed and returns to its original shape. So when we speak of such forces in this chapter, we mean the average force. We mean the average force. So we're increasing the change in momentum by manipulating the impulse, the force times time. All right, we'll get there. Just hang in. The force of impact on a golf ball varies throughout the duration of impact. In other words, look and see how it's distorted. You know, I have a very small impact time, but it's producing an enormous force, and you have a large change in momentum as a result of that, because you're taking this mass, relatively small mass, but you're speeding it up. Now let's talk about, a constant momentum going to zero, so you're going to have a change in momentum, and that change in momentum is going to be, you're going to hit that haystack. Are you going to stop quickly, small time, or large time? Well, what will increase the time it takes for the momentum to be used up? Well, the haystack will. Okay, the haystack is going to use it up. It's going to increase the time to use up that momentum. Now, so you're going 60 miles an hour, you're going 90 kilometers per hour in this big car, it's SUV, and you hit a haystack. Well, you'll come to a stop very, very slowly relative to hitting a brick wall. Now, look at the interior of an old car. There's no seat belts. There's no airbags. Where are you going to put the airbag? In a little tiny horn in the middle of the steering wheel? Here's a inside of a newer car. You have airbags in the passenger side, in the steering wheel. You have seat belts. You have padded dashboards. You have crumple zones in the front of the car. You know, you hit a car in the 1960 Chevy, you hit a telephone pole, you took the telephone pole, and you didn't even know you crashed into one because it was unbelievable. You didn't have any crash zones. No crash zone in this car. Look at that padded dash, or the lack of it. There's no padded dash. There's no airbag. Look at this. Look at this guy here getting hit by a punch, a boxer. He's going with the punch. Hard to tell in that small picture, but he's going with the punch. So the guy's punching, and he's going backwards. So he's not leaning into that punch. So the amount of time is high T on the right, small t, high T, small t, high T, small t. That guy's going right into the punch. He's leaning into that punch. When you box, you want to catch the boxer leaning toward you, and then it's terrible. It's very damaging. Look at this: small f, large T. The change in momentum. The fist is the fist. It's going to have a certain momentum. It's going to change the momentum. Is it going to change it slowly, or is it going to change it quickly? Left, slow change in momentum. Right, fast change in momentum. Change is the same. The time in which that momentum is being changed is different. What's the impact time? Large impact time, small impact force. Large impact time, small impact force. Look at the right. It's going to be large F, small t. Large F, small t. Large F, small t. Wait for it. Here it comes. Large F, small t. So the impulses, the one on the left and the one on the right, they're equal. But the one on the left is far less destructive. You have a large T. Look at this dog. Can you imagine if this dog was not restrained with a humane harness? That dog would bounce all around the car. It would be very damaging for the dog. And what about the people sitting in front of these two dogs? Their heads would be taken off. You have this literally dog cannonball going right up through the front windshield. You don't want to damage the dog. What happens when this car that has a mass and a large V hits that wall? What's going to happen? It's not going to be pretty. It's going to be a small t. It's going to be a small t, large F. A padded dashboard in a car is safer than a rigid metal one, and that airbag saves lives. You also know that to catch a fast-moving ball safely with your bare hand, you extend your hand forward, so there's plenty of room for it to move backwards after making contact with the ball. When you extend the time of contact, when you extend contact time, impact time, you reduce the force of the catch. Everybody's, you catch a ball and you move with it, and you are doing what? You are reducing the force of the catch. You're reducing the impact time. You're increasing the impact time and reducing the impact force. Impact force, impact time. Large impact time, small impact force. So that's the way to do it. And this is what happens. If you have a small t, you're going to have a large F. Terribly destructive. People don't realize the reason people are injured in car accidents is because of physics, is because of molecular theory. You're just simply, the car could be thought of a giant molecule, and it's an inelastic collision. So we're going to have to look at elastic collisions. When a moving billiard ball, pool ball, collides head-on with a ball at rest, the first ball comes to rest and the second ball moves away with a velocity equal to the initial velocity of the first ball. We see that momentum is transferred. Now we're transferring momentum from the first ball to the second ball. When objects collide without being permanently deformed or without generating heat, the collision is said to be elastic. Colliding objects bounce perfectly in perfect elastic collisions. Note that the sum of the momentum vectors is the same before and after each collision, be that in a gas with molecular collisions, molecular theory, kinetic theory of gases. What's happening when that molecule hits the wall of the container? Is it a real gas or is it an ideal gas? Is there heat transferred? Why is that beaker hot when you touch that? What's heat? What is that? You're going to have those collisions of those molecules hitting the sides of the container and producing tremendous amounts of heat. Yes, I know, it's elastic collisions, but what is the difference between real and ideal gases? It's the type of collision. Is it an elastic collision or is it an inelastic collision? So, real versus ideal, elastic or inelastic versus elastic, real versus ideal, inelastic versus elastic. It's all about the collision. It's all about momentum. It's all about the physics. Chapters 13 and 14, states of matter and gases, it's all about the physics of the molecules, the physics of the environment. When the cylinder has a volume, we're going back now to where we were, when the cylinder has a volume of 1 liter, the gas exerts a pressure of 100 kilopascals. When the volume is halved to 0.5 liters, the pressure is doubled to 200 kilopascals. Increasing the volume of the contained gas has the opposite effect. If the volume is doubled, the particles can expand into a volume that is twice the original volume. With the same number of particles in twice the volume, the pressure of the gas is cut in half. So now we're going back to where we were. But remember, in order to understand a chemical reaction, you have to understand the physical environment. It is important to understand some of the physics. So we do some physics in chemistry. Not a lot, but a significant amount. An increase in temperature causes an increase in the pressure of an enclosed gas. The container can explode if there is too great an increase in pressure. Look at the temperature changes. Look at the pressure changes. Whoa. 600 K, 200. So it must be 200 to 400 would be 1200. So we're talking about hot, and that's 500. That's not even 400. A sealed bag of potato chips bulges at the seams when placed in a sunny location. The bag bulges because an increase in the pressure, an increase in the temperature of the enclosed gas causes an increase in its pressure. You can use kinetic theory to explain what happens. As a gas is heated, the temperature increases and the average kinetic energy of the particles in the gas increases. Faster moving particles impact the walls of their container with more energy. Gay Lussac's law. Pressure versus temperature, it's direct with a constant volume. The slide before that was Boyle's law. Pressure, volume. Pressure, volume. Indirect. Look at figure 7. The volume of the container and the amount of gas is constant when the Kelvin temperature of the enclosed gas doubles from 300 to 600. The pressure of the enclosed gas doubles from 100 kilopascals to 200 kilopascals. A gas in a sealed container may generate enormous pressure when heated. All of a sudden the volume has to change. All of a sudden now we're in combined gas laws where there's going to be a change in volume. It just simply explodes. For that reason, an aerosol can, even if it's empty, may explode if thrown into a fire. By contrast, as the temperature of an enclosed gas decreases, the pressure decreases. The particles on average move more slowly and have less kinetic energy. They strike the container walls with less force, halving the Kelvin temperature of a gas in a rigid container decreases gas pressure by half. Decrease pressure, decrease temperature. Increase pressure, increase temperature. Boyle's law, that's Gay Lussac's law. Boyle's law from a few slides before. Increase pressure, decrease volume. Decrease pressure, increase volume. Here's another one with Boyle's law. How would an increase in pressure affect the volume of a contained gas? If the temperature is constant, Boyle's law, as the pressure of gas increases, the volume decreases. In turn, as the pressure decreases, the volume increases. P3V3, P1V1, P2V2, P3V3 equals P1V1, etc. Robert Boyle was the first to study this pressure-volume relationship in a systematic way. In 1662, Boyle proposed a law to describe the relationship. Boyle's law stated that for a given mass of gas at constant temperature, the volume of the gas varies inversely, indirectly with the pressure. So, P3V3 equals P1V1. P times V. P3V3, P3 times V3 equals P1 times V1. Product constants. Product constants. A product constant equals or is the same as an indirect mathematical relationship. Indirect. Look at figure 8. A gas with a volume of 1 liter, V1, is at a pressure of 100 kilopascals, P1. As the volume increases to 2 liters, V2, the pressure decreases to 50 kilopascals, P2. The product, P1 times V1, or 100 kilopascals times 1 liter, equals 100 kilopascal liters, is the same as the product P2 equals V2. 50 kilopascals equals 2 liters equals 100 kilopascal liters. Boyle's law. Boyle's law. We've looked at Gay Lussac's law. We're looking currently at Boyle's law. As the volume decreases to 0.5 liters, V3, the pressure increases to 200 kilopascals, P3. Again, the product of the pressure and the volume equals 100 kilopascal liters. Now, figure 9 compares the volume of a balloon in a mixture of ice, salt, and water to the volume of the same balloon in hot water. The amount of gas and the pressure are constant. As the temperature of an enclosed gas increases, the volume increases if the pressure is constant. Charles' law. Volume and temperature are direct. In 1787, the French physicist Jacques Charles studied the effect of temperature on the volume of a gas at constant pressure. When he graphed his data, Charles observed that a graph of gas volume versus temperature in degrees Celsius is a straight line for any gas. Is a straight line for any gas. When he extrapolated or extended the line to 0, volume, V equals 0, the line always intersected the temperature axis at negative 273.15 degrees Celsius, absolute 0. This value is equal to 0 on the Kelvin temperature scale. The observations that Charles made are summarized in Charles' law. Charles' law states that the volume of a fixed mass of gas is directly proportional to its Kelvin temperature if the pressure is kept constant. Look at the graph in figure 10. When the temperature is 300 Kelvin, the volume is 1 liter. When the temperature is 900 Kelvin, the volume is 3 liters. In both cases, the ratio of V to T is 0.0033. 0.0033. The ratio V1T1 is equal to the ratio V2 over T2 because this ratio is constant at all conditions of temperature and volume. When the pressure is constant, you can write Charles's law as follows. The ratio of the variables is always a constant in a direct relationship, and the graph is always a straight line. It is not a direct relationship if the temperatures are expressed in degrees Celsius. So, when you solve gas law problems, the temperature must always be expressed in kelvins. When tires are not inflated to recommended pressure, fuel efficiency and traction decrease. Treads can wear down faster. Most importantly, improper inflation can lead to tire failure. A driver should not check tire pressure after driving a long distance because the air in the tire heats up during a drive. As the temperature of an enclosed gas increases, the pressure increases if the volume is constant. Again, now we're talking about volume and temperature or pressure and temperature. Aha, Gay Lussac's law. Joseph Gay Lussac, 1778 to 1850, a French chemist, discovered the relationship between the pressure and temperature of a gas in 1802. His name is on the gas law that describes the relationship. Gay Lussac's law states that the pressure of a gas is directly proportional to the Kelvin temperature if the volume remains constant. Gay Lussac. Pressure and temperature are direct. I double the temperature, I double the pressure. 300 Kelvin to 600 Kelvin, 100 kPa to 200 kPa. Look at figure 11. When the temperature is 300 K, the pressure is 100 kPa. When the temperature is doubled to 600 Kelvin, the pressure doubles to 200 kilopascals, because Gay Lussac's law involves direct proportions. The ratios P1 over T1 equal and P2 over T2 are equal at constant volume. Constant volume. You can write Gay Lussac's law as follows. The green, P1 over T1, P2 over T2. Gay Lussac's law can be applied to reduce the time it takes to cook food. One cooking method involves placing food above a layer of water and heating the water. The water vapor or steam that is produced cooks the food. Gay Lussac's law. The temperature of the steam reaches about 120 degrees Celsius. The food cooks faster at this higher temperature, but the pressure rises, which increases the risk of an explosion. A pressure cooker has a valve that allows some vapor to escape when the pressure exceeds the set value. The temperature of the steam reaches about 120 degrees Celsius. The food cooks faster at this higher temperature, but the pressure rises, which increases the risk of an explosion. The pressure cooker has a valve that allows some vapor to escape when the pressure exceeds the set value. I wanted to kind of repeat myself in case you ever use a pressure cooker. I used to live in Africa where we had to use pressure cookers, and every once in a while you'd read about somebody using a pressure cooker that exploded, and you got to be careful. You got to make sure that valve is on so that the steam can escape. So here's Charles' law, where pressure is constant, so pressure cancels out. P1 equals P2, and it's going to be V1 over T1 equals V2 over T2, and that's Charles's law. Charles's law. French guy, Jacques Charles. Charles was actually responsible for getting a lot of Gay Lussac's law published, because Gay Lussac died kind of prematurely, and Charles kind of helped out with that. Boyle's law, T1 equals T2, so the T's cancel, and you're left with P1 V1 equals P2 V2. Boyle's law, T1 equals T2, so they're the same on either side, so they cancel. So if it was 2 and 2, it would cancel. Okay, Gay Lussac's law, V1 equals V2. So there you have it. P1 over T1 equals P2 over T2. P1 over T1 equals P2 over T2. So all you have to do is really know the combined gas law. P1 V1 over T1 equals P2 V2 over T2. And if you know the combined gas law, all the other ones become very easy. With the combined gas law, you can solve problems with 3 variables: pressure, volume, and temperature. The combined gas law assumes that the amount of gas does not vary. You cannot use the combined gas law to calculate the number of moles of a gas in a fixed volume at a known temperature and pressure. To calculate the number of moles of a contained gas requires an expression that contains the variable n. The combined gas law can be modified to include the number of moles. The combined gas law can be modified to include the number of moles. So we need to come up with an equation where we're using moles. So that's going to be another equation that we're going to actually come up and use eventually. The number of moles of a gas is directly proportional to the number of particles. The volume occupied by a gas at a specific temperature and pressure must also depend on the number of particles. So moles must be directly proportional to volume as well. You can introduce moles into the combined gas law by dividing each side of the equation by n. This equation shows that PV over Tn is a constant. So now we're getting down to it. This constant holds for ideal gases, gases that conform to the gas laws. If you know the values of P, V, T, and N for one set of conditions, you can calculate a value for the constant. Recall that 1 mole of every gas occupies 22.4 liters at STP 101.3 kilopascals and 273 Kelvin. You can use these values to find the value of the constant, which has the symbol R and is called the ideal gas constant. Insert the values of P, V, T, and N into the ideal gas constant. R has the value 8.1 kilopascal liters over Kelvin moles. Because it's 101.3 times 22.4 divided by 273.15 divided by 1, and that's your value. The ideal gas constant R has a value of 8.31 liter kilopascal divided by Kelvin moles. The gas law that includes all 4 variables, P, V, T, and N, is called the ideal gas law. Now, this law is going to be very, very, very important, and it is usually written as follows: PV equals nRT. P for pressure, V for volume, N for moles, R is the ideal gas constant, 8.31 liter kilopascal over Kelvin moles, times T, which should be in Kelvin. Kelvin, what are the unit labels? Well, look at the unit labels for R. You don't know the unit labels for R? Well, P is kilopascals, V is liters, and T is Kelvin. and N is moles. Using the ideal gas law to find the amount of a gas. A deep underground cavern contains 2.24 times 10 to the 6 liters of methane gas at a pressure of 1.5 times 10 to the third kilopascals and a temperature of 315 Kelvin. How many kilograms of methane does the cavern contain? Analyze the list of knowns and the unknown. There are the knowns. I just read them off. The molar mass of methane, 12 for carbon, 4 for hydrogen, 16. And we want to know the mass in kilograms of methane. So we're looking for the mass, not the molar mass. Molar mass is given. Okay, in other words, I could list that as 16 AMUs. Same thing. But now I want to find the mass in kilograms. Calculate the number of moles using the ideal gas law. Use the molar mass to convert moles to grams, then convert grams to kilograms. Rearrange the equation for the ideal gas law to solve for N. Now, N equals PV over RT. Plug in for P, plug in for V, plug in for R and T, and then make sure the unit labels, make sure that P is in kilopascals, V is in liters, etc. And you get 1.28 times 10 to the 6th moles. 1.28 times 10 to the 6th moles. Now, that value, 1.28 times 10 to the 6th moles, is going to equal the mass over the atomic weight. Well, I know the atomic weight. It's going to be 16. 16 AMUs, or the molar mass of 16. I could say over the atomic weight or over the molar mass. Same thing. So, 1.28 times 10 to the 6 moles equals mass in kilograms over 16 AMUs. Mass equals 1.28 times 10 to the 6 moles times 16. Mass equals 2.05 times 10 to the 7th grams. 2.05 times 10 to the 7th grams. So, what am I going to do now in terms of, well, I got to convert it to kilograms. Divide by 1,000, I get 20,500 kilograms. Does the result make sense? Although the methane is compressed, its volume is still very large. So, it is reasonable that the cavern contains a large mass of methane. An ideal gas is one that follows the gas laws at all conditions of pressure and temperature. Such a gas would have to conform precisely to the assumptions of kinetic theory. Its particles could have no volume, and there could be no attraction between particles in the gas. In this flask used to store liquid nitrogen, there are two walls with a vacuum between them. As you probably suspect, there is no gas for which these assumptions are true. So, an ideal gas does not exist. Nevertheless, at many conditions of temperature and pressure, real gases behave very much like ideal gases, especially around and on Earth. Within reason, gases can act very ideal-like within a certain range of temperatures. The particles in a real gas do have volume, and there are attractions between the particles. Because of these attractions, a gas can condense or even solidify when it is compressed or cooled. For example, if water vapor is cooled below 100 degrees Celsius at standard atmospheric pressure, it condenses to a liquid. So, that's proof that it is not ideal, but it is real. Figure 15 shows how the value of the ratio PV over nRT changes as pressure increases. For an ideal gas, the result is a horizontal line because the ratio is always equal to 1. For real gases at high pressure, the ratio may deviate or depart from the ideal. When the ratio is greater than 1, the curve rises above the ideal gas line. When the ratio is less than 1, the curve drops below the line. The deviations can be explained by two factors. And attractive forces reduce the distance between particles. A gas occupies less volume than expected, causing the ratio to be less than 1, but the actual volume of the molecules causes the ratio to be greater than 1. In portions of the curves below the line, intermolecular attractions dominate. In portions of the curve above the line, molecular volume dominates. So, you can see why in order to learn the nature of gases, we simplify it by saying, okay, well, let's learn ideal gases first, and then we'll worry about real gases relative to some of the inherent forces involved. In portions of the curve above the line, molecular volume dominates. Look at the curves for methane at 0 degrees and 200 degrees Celsius. At 200 degrees Celsius, the molecules have more kinetic energy to overcome intermolecular attractions. So the curve for methane at 200 degrees Celsius never drops below the line. It never drops below the line. So it's pretty important. Methane is the gold or the yellow line. So you can see how that stays above that line. So it can become rather complicated. Now, gas pressure results from collisions of particles in a gas with an object. If the number of particles increases in a given volume, more collisions occur. If the average kinetic energy of the particles increases, more collisions occur. In both cases, the pressure increases. So you can see the substance, and then you can see the volume component in terms of percentages and the partial pressures of each. So it's pretty amazing. Gas pressure depends only on the number of particles in a given volume and on the average kinetic energy. Particles in a mixture of gases at the same temperature have the same average kinetic energy. So the kind of particle is not important. Table 1 shows the composition of dry air, air that does not contain any water vapor. So the volume component and the partial pressure are strangely equivalent. The contribution each gas in a mixture makes to the total pressure is called the partial pressure exerted by that gas, or the partial pressures for short. In dry air, the partial pressure of nitrogen is 79.11 kilopascals. In a mixture of gases, the total pressure is the sum of the partial pressures of the gases. Okay, P total equals P1 plus P2 plus P3, etc. This equation is a mathematical expression of the law proposed by Dalton. Dalton's law of partial pressure states that at constant volume and temperature, the total pressure exerted by a mixture of gases is equal to the sum of the partial pressures of the component gases. That's a mouthful. So, but it's actually both simple and a little confusing. Here's an example. 3 gases are combined in container T. The pressure that each gas exerts is independent of the pressure exerted by the other 2 gases. Now, we're talking about ideal gas laws, essentially, aren't we? The pressure in container T is the sum of the pressures in containers A, B, and C. So container T, T for total, is going to be the sum. Look at figure 16. Containers A, B, C, and T, for total, have the same volume and are at the same temperature. The gases in containers A, B, and C are combined in container T. Because the volumes are identical, each gas in the mixture exerts the pressure it exerted before the gases were mixed in container T. So the pressure in container T, 550 kilopascals, is the sum of the pressures in containers A, B, and C. 100 plus 250 plus 200 kilopascals. If the percentage composition of a mixture of gases does not change, the fraction of the pressures, sorry, I had to change the timing. Where were we? The fraction of the pressures exerted by a gas does not change as the total pressure changes. So, the fact that the green gas and the red gas and the purple gas all equal the total gas, because they don't know. I could have chlorine, oxygen, and fluorine, and they don't realize what kind of gas each other is. They all have blindfolds on. They're all the same. All the gases are exactly the same, and they don't recognize. There's no physically anyway, there's no difference between chlorine and oxygen in terms of treating gases in an ideal behavior. The fact is important for people who must operate at high altitudes. For example, at the top of Mount Everest, the total atmospheric pressure is 33.73 kilopascals. Water is not going to boil at 100 degrees Celsius, trust me. This is about 1/3 of the value at sea level. The partial pressure of oxygen is also reduced by 1/3, or 7.06 kilopascals. The partial pressure of oxygen must be 10.67 kilopascals or higher to support respiration in humans. The climber in Figure 17 needs an oxygen mask and a cylinder of compressed oxygen to survive. A lot of people die up in Mount Everest, so you gotta be in shape and you gotta make sure you take your gases with you. Look at this guy. He looks kind of like Snoopy from the Peanuts cartoon. Either that or a really strange alien. This climber is using a tank of compressed gas to supplement the supply of oxygen available at high altitudes. You get altitude sickness. You know, you have to allow your body to adjust. They have various base camps at various altitudes that allow themselves to acclimate to lower oxygen partial pressures and allow them to make the ascent to Everest without dying. The relative partial pressures exerted by a gas in a mixture of gases does not vary with temperature, pressure, or volume of the mixture. The ratio of N1 over N, the relative amount of the gas in the mixture, remains the same because the value of N1 over N remains constant. The relative partial pressure, P1 over P, exerted by the gas remains the same. Firefighters carry tanks of compressed gas. The tanks contain from 19.5% to 23.5% oxygen by volume. You know, why don't they use more oxygen? Well, they're in a fire. You don't want to have too much oxygen. They would explode. So you're going to, contain a gas that's relatively the same as air. It's not too much different. The diffusion, let's talk about diffusion, Graham's law of diffusion. The diffusion of one substance through another is a relatively slow process. Bromine vapor is diffusing upward through air in a graduated cylinder. After several hours, bromine vapors are near the top of the cylinder, predicting what will happen as the bromine continues to diffuse. Well, what's the difference between diffusion and effusion? That's another one. Suppose you open a perfume bottle in a corner of a room. At some point, a person standing in the opposite corner will be able to smell the perfume. Molecules in the perfume evaporate and diffuse or spread out through the air in the room. Diffusion is the tendency of molecules to move towards area of lower concentration until the concentration is uniform throughout. In figure 18a, bromine vapor is diffusing through the air in a graduated cylinder. So what's going to happen as it continues to diffuse? The bromine vapor in the bottom of the cylinder has started to move upward towards the area where there is a lower concentration of bromine. In figure 18b, the bromine has diffused almost to the top of the cylinder. If the process is allowed to continue, the bromine vapor will spill out of the cylinder. There is another process that involves the movement of molecules in a gas. This process is called effusion. During effusion, listen carefully, a gas escapes through a tiny, tiny hole in its container. With effusion and diffusion, the type of particle is important. Gases of lower molar mass diffuse and effuse faster than gases of higher molar mass. Thomas Graham's contribution, the Scottish chemist Thomas Graham, studied rates of effusion during the 1840s. From his observations, he proposed a law. Graham's law of effusion states that the rate of effusion of a gas is inversely proportionate to the square root of the gas's molar mass. This law can also be applied to diffusion of gases. Graham's law makes sense if you know how the mass, velocity, and kinetic energy of a moving object are related. The expression that relates the mass m and the velocity v of an object to its kinetic energy, Ke is, the kinetic energy is, Ke, kinetic energy, equals 1/2 mv squared. Let me change the timings on this. Let me just reset this. I'll be right back. Okay, I would never have made it through this. I'm glad I changed the timings. Okay, I think we were where? For the kinetic energy to be constant, any increase in mass must be balanced by a decrease in velocity. Very important. For the kinetic energy to be constant, any increase in mass must be balanced by a decrease in velocity. For example, a ball with a mass of 2 grams must travel 5 meters per second to have the same kinetic energy as a ball with a mass of 1 gram traveling 7 meters per second. There is an important principle here. If two objects with different masses have the same kinetic energy, the lighter object must move faster. Look, very confusing. We did that very quickly. We'll take our time looking at the equations, and maybe we'll do a sample problem for this. So stay tuned. Okay, let me check the timings of this. We're almost done, and be right back. Okay, the balloon in figure 19, I think that's Garfield, is used in holiday parades. It is filled with helium so that it will float above the crowd along the parade route. There is a drawback to using helium in a balloon. Both helium atoms and the molecules in air can pass freely through the tiny pores in a balloon. But a helium-filled balloon will deflate sooner than an air-filled balloon. Kinetic theory can explain this difference. If the balloons are at the same temperature, the particles in each balloon have the same average kinetic energy. But helium atoms are less massive than oxygen or nitrogen molecules. So the lighter the molecules, the faster it's going to move. The lighter the molecules, so helium will move very quickly. So the molecules in air move more slowly than helium atoms with the same kinetic energy, because the rate of effusion is related only to a particle's speed. Graham's law can be written as follows for two gases A and B. The rates of effusion of two gases are, listen carefully, inversely proportional to the square roots of their molar masses. So let's look at the equation and see if we can maybe make some sense out of it. Let's, here it is, okay. Velocity, here it is. Velocity gas A divided by velocity gas B equals the square root of molar mass gas B over molar mass gas A. Compare the rates of effusion of helium to nitrogen. So you got to pick one, and then you just do the opposite. Okay. Velocity gas A over velocity gas B is 2.7 to 1. Now you could say 1 to 2.7, but that would be a little weird. So you just make sure that the larger one is on top, so it's a number greater than 1. Otherwise, it gets a little confusing. So that's it. And have a great night. And make sure you study this weekend. And goodbye.